I will show you a comparison between two measurement techniques in order to identify an equivalent crack size for applying fracture mechanics approach to estimate the fatigue limit of a titanium alloy specimen in as-built surface conditions. So here we are using a fracture mechanic approach that is based on the Hattori-Lazzari-Meneghetti model that is an extension of the classical Kitagawa-Takahashi diagram, in which for this case, when we deal with the effects in additively manufactured materials, the diagram collapses in the model well known of Eladad, Smith, Topper. When we deal with additively manufactured materials in post-heat treatment conditions, we have two different scenarios. If we machine the specimens, the fatigue limit of this condition is well correlated with the distribution of the killer defects that are easily measurable from the fracture surface analysis by using, for instance, the square root of area parameter proposed by Murakami. When we deal with as-built surface conditions, the fatigue limit is not well known correlated with any kind of size, because due to the very irregular and pseudo-randomic profile of the surface. So dealing with this aspect, many researchers suggest in using the areal roughness parameter to deal with the fatigue analysis of the manufactured material in as-built conditions. In particular, here we have an example of a measurement performed by an optical profiler, where the color represents the height of the profile of the surface. And in this reference, it was seen that the parameter that can be extrapolated from this measurement according to the relevant standard is the best one that correlates the fatigue limit of this material in these conditions. So the parameter is the SD, and it is defined as a maximum peak depth within a control area. So for instance, if this one is our control area, we need to define the maximum peak depth that in this case, if we see the scale, would be 60 micrometers. According to the definitions, we measure this depth in a control areas, but if we are interested in the maximum pit depth within a region where subjected to the maximum applied stress amplitude, such as, for example, the gauge part of a cylindrical specimen depicted in these slides, we can extrapolate the maximum volume by using the stream value statistics, and using this value combined with an assumption of equivalent initial crack for estimating the fatigue limits of our material. But why so many researchers suggest areal measurement techniques rather than the well-known profile measurement techniques? Due to this is because mainly on the domain of the measurement. So the areal measurement investigate an area, and we can extrapolate the information in a larger area. The profile measurements extract the information, maybe represented by the RV parameter, that is a parameter that has a definition equivalent to the relevant previous areal parameter SV in a profile, and we cannot extract this information to estimate what could be the maximum pit depth within the gauge part of our specimen. So here is the question that we want to answer, if this parameter can be used together with extreme value statistics for obtaining the same SV max by using areal measurements. So the trick is this one. We take inspiration from the method of the polytest section for estimating the maximum defect size within a volume proposed by Murakami. Here we have the two reference in which this method is explained. And the method consists in evaluating the distribution of the square root of area of the defects on a polished sections. And extrapolate this formation by multiplying the size of the area of the inspection by the called H, that is the average value of the square root of area measured in the control areas A0. So if we have information in the one-dimensional domain, like the RV parameters extracted from a profile, we can take inspiration from this approach to extend this profile to an area investigation by multiplying the control lines by the H value, that is in this case is the average value of the RV measured in several profiles. So we wanted to demonstrate that, and we used several fatigue test data that we performed in a previous work on a titanium alloy specimen with the vertical direction of printing in annealing condition. Here we have the statical mechanical properties of the material, and the tests were conducted with a stress load ratio equal to -1 in a stress control mode. The material properties of our material considered were estimated by using empirical equation described and proposed in these two papers. So defining the fatigue limit of ideally defect-free materials, starting from the Vickers hardness of the material measurement, of course, on our specimens, and the delta K threshold for long cracks estimated by using a biparametric model based on a microstructural length parameter and the Vickers hardness. So by using, means of these two material properties, we can draw our estimating model of the fatigue limits of the material. About the surface measurements, we perform several areal measurements by using an optical profiler. We remove the curvature effect by applying a form removal in order to obtain a flat surface roughness measurements, and we extracted the SV values from 10 areas for each specimen analyzed. So for each specimen, we extracted 10 SV parameters to be analyzed with the largest extreme values distributions. From these measurements, we also extracted 3 linear profile on the gauge length of the specimens for obtaining the RV parameter. And of course, with this parameter, we applied the trick that I explained before to obtain the relevant largest extreme value distribution to be compared with the previous one. So let's have a look on the number. Here we have the distribution, the Google distribution fitted over the SV measurements of our specimens. So I repeat, we have 10 SV values times 8 specimens. We had 8 specimens analyzed in this work. But with this distribution, this distribution doesn't help us to extract or to use any kind of fraction mechanics approach to estimate the fatigue limits. So we would need a distribution of the killer pit of our surface of our specimen batch. So here we extend or extrapolate such as a distribution by calculating the return period that is defined as the ratio between the reference area, that is the the surface area of the gauge part of the specimens, over the control areas analyzed for extracting the SV values. By using this relationship, we can shift these distributions on the right for obtaining the estimated Gumbel distribution of the killer pits of the batch of specimens. So here we have the distribution that will be used for estimating our fatigue limits. In the case of the linear profile measurements, we extracted the same distribution by calculating the control area starting from the control lines multiplied by the average value of the RV values extracted from the profiles, and we obtain the relevant estimated distribution. Here we have the result of the experimental fatigue limits. The fatigue limits in terms of stress range was 594. And what we observed in the high cycle fatigue regime is reported here in the fracture surfaces. In particular, the fracture starts just from a single point that is highlighted in these two pictures. And we don't observe any porosity or subsurface defects, so we are pretty confident that the cause of the failure was the pit of the surface. Here we have the estimated material models. We can plot the experimental fatigue limit to estimate what could be the effective crack length of our model. If we put the distribution that we obtain from the aerial measurements by assuming initial equivalent crack size shape as a semicircular, we can see the comparison between the fatigue limit. Here we have the distribution mapped on the fatigue limit axis, and as you can see, the 15 percentiles of the estimated fatigue limit is well agree well with the experimental fatigue limit obtained in our specimens. If we plot also the distribution coming from the RV values, as you can see here in these slides, here we have the comparison between the two distributions. That's the difference in terms of fatigue limits in the 15 percentiles on 6%. And the difference between the two distribution from the experimental values is quite low, so the 3.8 for the RV values and minus 1.9 for the SV values. So concluding, we apply the fracture mechanics approach for estimating the fatigue limits of as-built titanium alloy specimens. We define a sort of compatibility for analyzing also the profile measurement of the roughness of as-built additively manufactured materials. And we see that our estimation of the fatigue limits is quite good compared with the experimental values obtained in our specimens. So I conclude. Thank you for the attention.
So we are running a little bit out of time. Thank you very much. We have time for one question, if there is. Please.
Thank you for the nice presentation. Have you compared the killer defects that you have predicted with the experimental ones that you have got during the experimental test?
No, we don't. We didn't compare the experimental killer pit, let's say that, because it's quite difficult to take the reference line from, for instance, a fracture surface analysis like this one. So here I have just highlighted what could be the pit that originates the fractures surfaces. But according to the definition of SV, we need to know where is the reference line to calculate the depth of our pit. So it's a little bit tricky to measure this kind of parameter from fracture surfaces. So we have applied what we know from the defects, so from machined specimen where the defects are clearly visible and measurable on the fracture surfaces, to this kind of, let's say, pit or surface defects.
Okay, thank you.